Thank you very much, Antonio, for the introduction, and also as an organizer, together with Gregos and Vera, and perhaps last but certainly not least, Damien. Thank you very much for the invitation to come here and take part in this wonderful meeting and to present some work to you. So I should say that this will be a bit of a whistle-stop tour of some recent work in Banach space theory and applications to operator theory. And so I'm definitely not trying to be encyclopedic. Rather, I'm trying to give hopefully an introduction to people who haven't really looked at this cycle of problems. So I know some of you will know absolutely everything and much more than what I'm going to talk about, but I think many of you will not have looked very much at any of these things. So in particular, I hope to also give an introduction to this relatively recent method of constructing lots of operator ideals on Banach spaces due to Johnson and Schechtman. So fingers crossed we'll get there in time. I know it's a bit of a kamikaze style to try and lecture using chalk and talk, but I decided I don't have chalkboards in Lancaster where I usually teach, so I'm completely out of shape at doing this, but I kind of enjoy it. So I thought, let's give it a go. Anyhow, so what I decided to do a bit of pre-writing in order to speed things up. So what I'm going to talk about is joint work with my student, James Smith, who is in the process of writing up his PhD. So the first installment of it appeared earlier this year in Journal of Mathematical Analysis and Applications. And our work, so this is about these Baernstein and Schreier spaces, and it's building on previous work I did with Kevin Beanland and Thomas Kania. That appeared in Journal of Functional Analysis in 2020. And also we are relying heavily on some work from 2000, from Studia Mathematica by Gasparis and Lung. But we'll get to that later. And also, here are a few conventions that I'm going to use. So first of all, whenever I say operator, I mean a bounded and linear map between Banach spaces. And B of xy will be the operators from x to y. As usual, when x and y are equal, it's just B of x. Ideal, well, my ideals will always be closed, two-sided algebraic ideals. So apologies to those who are into Banach lattices. There'll be no order ideals here. My ideals are strictly from the algebraic side of things. K will be my scalar field, can be either real or complex numbers. I write square brackets of n for the infinite subsets of the natural numbers, and then with less than infinity for the sets. All right, and then finally, my convention is, so I'll be looking at a Banach space E, say, with a basis, usually just a unit vector basis En, and then I'll be looking at the subspaces that this are spanned by subsequences of this basis. So I'll just write En for the subspace spanned by the basis vectors coming from such a subset N. All right, so that was where we start. Now, let's see. So the starting point of all this was that we wanted, in the work with Tomek and Kevin, we wanted to understand the operator ideals on the Sielson space. And this goes back, I think, about 10 years now. And we succeeded to some extent. At least we managed to show that there are lots of them. In particular, there are at least continuum mini-maximal ideals. There are uncountable chains. So all sorts of strange things happen. And I think it's fair to say a full classification is certainly unrealistic here. So that was what we did. But what we were doing, so we were working with the Sielson space, that was our focus. But then at some point, I think Kevin observed that there was this paper by Gasparis and Lung where they had what we call a numerical index. They used to study subspaces of the Schreier spaces, so subspaces of this kind here spanned by subsequences of the unit vector basis, and actually it looked like it was sort of similar to what we were doing for the Sielson space, because we were also using a kind of index. It wasn't very explicit to begin with in our work, but we then kind of teased it out, and it actually turned out that the two methods were kind of parallel, and we thought that was nice. And so I thought when James started his PhD, then I proposed to him that we could try and do the same thing for the Baernstein spaces. And so that's basically what I want to talk about here. Okay, so let's see. So let me just go back to the very beginning of the Schreier spaces. So the start of this is nearly 100 years ago. Banach and Sachs proved that whenever you have a weakly convergent sequence in capital LP, so the Lebesgue spaces for P in the reflexive range, then you can pass to a subsequence of it, and the Cesaro means of that subsequence converge in norm. So the Cesaro mean of a sequence is just you add up the first n terms, and then you divide by n. Okay, so that was the theorem of Banach and Sachs. And then they asked what happens if you, instead of these Lebesgue spaces, you look at the continuous functions on the unit interval. And Schreier immediately sprang into action, and he proved that the answer is no. In other words, the result is false there. In fact, if you look at Schreier's proof, he worked with functions on the ordinal interval up to omega to the omega. So the first one after C, that's not isomorphic to C0, if you like. But there was no Schreier space explicit in this. However, the sets that bear Schreier's name were definitely in the paper, or a very close variant of them. So let me just try and explain to you what a Schreier set is. So say a subset, a finite subset of the natural numbers is a Schreier set if the minimum of A dominates its cardinality. And conventionally, people also consider the empty set Schreier set. For our purposes, that's not really very convenient, so let's just say that we rule that out for now. And then I will write such a script S here for the collection of all Schreier sets. These are the Schreier sets. In other words, when you construct Schreier sets, what you do is you choose the smallest element you want, and then after that you can choose that many elements, but no more. All right, so then given such a Schreier set and an element in a scalar sequence, we can now define, well, we can associate a seminorm with such finite sets just by taking x, and we sum up the coordinates according to elements in A, right? And since A is finite, this is obviously a finite number. Then what you do is you can now try and define a norm using this. So this is a normal S, is distinguished from that S there. Okay, so this will be the sup of all these seminorms as A ranges over all the Schreier sets. And of course, you may end up with plus infinity here, but if you rule that out, then you get what we call Z1. So if X is a scalar sequence for which this Schreier norm is actually finite, then you get a Banach space with respect to the coordinate-wise operations here on the scalar sequences and the norm that we have here. Okay, so that's what I call the big or the unrestricted Schreier space. Now, in order to actually get what's usually called the Schreier space, we have to go to the closure of C0. So in other words, the finitely supported sequences inside this space here. So this one here is in general not separable, but this one is an Oyster space, and this is the one that people normally call the Schreier space. All right. So curiously, this was not, as far as I can tell, defined explicitly in the literature until Bosami did so in 1979, so 50 years after Schreier's work, essentially. Anyway, so there is then, there are various ways you can generalize this. So the more conventional way that most people do, in particular that Gasparis and Lung also looked at, is the so-called higher order Schreier spaces, where you define inductively, you define higher order Schreier families. And so this is due to Alsbach and Argyros from the 1980s. And then you follow this definition here, but instead of taking sets from the first Schreier family, you take them from the higher order Schreier families. And in particular, in the work of Gasparis and Lung, they looked at all the higher order Schreier families of finite order, but you can actually do it for all countable ordinals. And I think Anna and Ryan Corsi have recently done some work on the infinite ones. But that's not where I want to go. And they were also, so we used the work of Gasparis and Lung in the paper with Beanland and Kanya to do work for these the higher order ones of finite order. But what I want to do instead here is I want to look at a slightly different generalization. Namely, now I want to take a P between 1 and infinity, and then I want to P-convexify. So I simply use the LP norm here to define my semi-norm. And then, of course, I get a different thing here if I put a little p here, but not there. All right, and then I get the, again, a non-separable space here. And I can get my P-convexified Schreier space as the closure of C00 inside here. Yes, 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 here, yes, here. That's why it's here, but not here because this is the Schreier family, right? No, S2 is a different family, is a different notion. Okay, well, this is just, okay, so my convention when I write norms is simply when I have a Banach space X with a norm, I normally denote the norm with a subscript X, if I want to distinguish it. Yes, when they P-convexify, yeah. Yes. Yes, you could do, yes. Absolutely. Lots of ways one can do these things. Anyway, so let's try and see. These P-convexified Schreier spaces, they are just the supporting cast here. The protagonists are the Baernstein spaces, so they are different. What's the origin of the Baernstein space? Well, by the 1960s, it was known that every super-reflexive Banach space has this property of Banach and Sachs. But also there are Banach spaces with that property that aren't super-reflexive. On the other hand, it was also known that every Banach space with the Banach-Sachs property has to be reflexive. But it wasn't known if all reflexive Banach spaces have the Banach-Sachs property. But Baernstein then wanted to answer that. And so what Baernstein did was he did a construction that was similar but somewhat more complicated. So basically, what we need to do is now we need to look at so-called Schreier chains. So by a Schreier chain, we mean a finite collection of Schreier sets. So n can be any number here, A1 up to AN are Schreier sets, and they should be consecutive in the sense that the maximum of the first is smaller than the minimum of the second, and so on and so forth. Okay, so that's what I call a Schreier chain. And then I mimic what I did before. Now I take a scalar sequence and I take a P. So let's see, we have X scalar sequence and we have P, but now it's important P is not equal to 1. Then we can define a seminorm associated with such a chain. So let's see, let's take C, one of these Schreier chains. And what we do is now we have a double sum. So we take A, one of the sets in the chain, then we sum over all the indices in A, and we take the absolute value of the nth coordinate, and we sum over all of those up. We raise this to the power P, and then outside here, we take 1 over P. And it's immediate, hopefully, that why I can't do this for p equal to 1. Well, I can do it, but then I just get the L1 norm back. So that's not interesting to do. Okay, and then we mimic what we did before. So now we define BP to be the collection of all scalar sequences that have finite BP norm. And this is then the pth. So this is a Banach space with respect to the BP norm. Okay, and so this is what's called the pth Baernstein space. Baernstein did this for p equal to 2, but then about 5 years later, Seifert, who was a student of Joe Diestel, I think, and other people at Kent State, he observed that you can immediately generalize it to all the other p's in the reflexive range. So this is what we call the pth Baernstein space. And what James and I wanted to try and do was to develop a theory of closed operator ideals, analogous to what Kevin Beanland and Thomas Kanya had done, and I had done in case of the Stilton space and these higher order Schreier spaces of finite order. So, in order to do this, well, maybe I should explain. So Baernstein, as I say, showed that this was reflexive and failed the Banach-Sachs property. But what's curious is, over here, I had an extra step. I had to pass to the closure of C00, but basically because this space is reflexive, we already know that C00 is dense. So we don't need to take that step. And the general convention that I use here is that E will either be one of these p-convexified Schreier spaces or the pth Baernstein space. So this is just to unify notation. And as I say, originally we did all this for the Baernstein spaces. That's what we are really interested in. But it turned out everything worked also for the p-convexified Schreier spaces, and generally the proofs were easier, and certainly for introducing this whole machinery, I think they're quite helpful, so we decided why not include them now we were working on it. Okay, so, and I believe much of this can also be done for higher order Schreier families, so you could have higher order Baernstein spaces and so on and so forth. We haven't gone down in that direction because then things get more technical. You have to do a lot of proofs on induction and so on, and this was already quite a substantial work to make everything work in the first case, and we just simply wanted to understand what results could you hope for. And it turns out that everything works very similar to the case that Gasparis and Lung studied. So let's just try and see what. Yes. So okay. So the fundamental fact that I'll be using over and over again is that if you look at the unit vector basis, so in other words, the En is the vector with a 1 in position n and 0 is everywhere else. So this is a shrinking and 1 unconditional basis for E. Of course, shrinking in the reflexive case is trivial, but not for the other ones. So, in other words, that's why I want to have that convention about subspaces up here. And so what Gasparis and Lung wanted to do was they wanted to understand complementary subspaces of the Schreier spaces, and they looked at the complementary subspaces of that particular form here, so spanned by subsequences of the basis. Because it's unconditional, they are indeed complemented. And the way they did it, although it's slightly hidden in their paper, but what I want to try and explain today, because I know there are lots of people here who are interested in, say, Banach spaces and combinatorics and set theory, and so I thought I wanted to highlight this combinatorial index that they used in their study, because I find that quite attractive, and I hope that will be of interest to some people. I think there's a lot more combinatorics than can be done on it. So, in order to define that, I need to introduce the Schreier covering number of a set. So, if you have, so take a finite subset of natural numbers, and then its Schreier covering number is tau 1 of A. Well, it's simply the smallest number of successive Schreier sets that you can cover it by. So A is contained in n Schreier sets. So B1 up to Bn are Schreier sets, and let's just say they are consecutive. Well, okay, so that's a Schreier covering number. And this is, I mean, you just essentially, when you're trying to calculate this, you can use the greedy algorithm, right? You have a subset, you take its minimum, that tells you what the maximal Schreier set you can start with is. You just take that many, say, you start at 5, then you can take the first 5 elements of A to put in there. Then you see the next element that you haven't covered yet. That tells you how many elements you can then put into your second set and so on. And you see how many steps you need to go, and that's your Schreier covering number. All right, so then we can define what we now call the Gaspari's Lung index, and we write gamma L 1 for it. So now we need, let me see, I should say, now we have 2 infinite sets here, M and N, and then of course there is a unique order isomorphism on one onto the other. So in other words, the unique increasing bijection from M1 to N. Okay, then you can define this Gaspari's Lung index of M with respect to N. So what is that? Well, it is the sup of the Schreier covering number of the pre-image in M of every Schreier subset of N. So in other words, you take a subset of your second set N, then you take a subset that's a Schreier set, all right? Then you pull it back to M, and you ask how many Schreier sets do you need to cover it now? And if there's a uniform bound on that, so that basically means that you're not filling in too many holes, right? The further out you are, and let's see to you out is that way, the further out you are, the longer your Schreier sets can be. And basically, in order that this index gets very big, it is if N is kind of quite sparse and M is very dense early on. That's the kind of operation you're not allowed to do here. So that gives you this Gaspari's Lung index. So I think Gaspari's and Lung just called it D1 or something like that. We thought that we should sort of highlight it and in particular honor Gaspari's Greek. Gamma is the first letter of Gaspari's in Greek, L for Lung, because we felt GL was kind of already taken by the matrix group people, right? So anyhow, that's a Gaspari's Lung index. And so let me just cite for you 2 main results that Gaspari's and Lung proved for E equal to S1, and also the higher order Schreier spaces of finite order. So let's see. So here we take, again, we take M and N to infinite sets. Then the first part says that the following are equivalent, that the Gaspari's Lung index of M in N is finite if and only if the subsequence of the unit vector basis indexed by M dominates the subsequence indexed by N, and if and only if, and this is a slightly technical condition, if and only if there is a spiky operator from the closed linear span of these guys into the closed linear span of these guys. And what does it mean that it's spiky? Well, it means that if you take the inf over M of the sup over N of the image of the mth basis vector of T, and now you take out the nth coordinate, then this will be uniformly bounded away from 0. So if I just ignore the inf here, right, this thing here, this is just the L infinity norm of the T of EM, right, the image of the mth basis vector. I'm just picking out the coordinates of it. And what this says is somehow, if you think of it as an operator into there, then it's quite spiky. So this is a slightly technical condition, but it looks much nicer if you symmetrize it. So let's try and do that. So the second part here is that also the following assertions are equivalent here, that if you now assume that both Gaspari's-Lung indices are finite, so in both orders, well, that's the same as saying, unsurprisingly from what we've just seen, that the two basic sequences here are equivalent, because that's what we know from the previous part. But now the third condition looks much nicer, because it simply says that the two spaces spanned by this one and this one are isomorphic. And this is really quite a surprising result, because it basically says that if these two Banach spaces are isomorphic, the way it happens is the most trivial way it can possibly happen, namely you can map the basis of this guy onto the basis of that guy. So that's really quite a surprising result, even though it may not look that much here. All right, so that was they were the tools Gasparis and Lung developed, and what they could get out of that was, in particular, they could show that no space of this form here is primary. So in other words, you can always decompose it as a direct sum of two infinite dimensional summons, and neither is isomorphic to the space itself. They also were able to construct a family of cardinality continuum of infinite subsets of the natural numbers, with the property that no two spaces in that family, so of the form En and Em, they are comparable. So in other words, En does not embed into Em, and Em does not embed into En. So there were loads and loads of complementary subspaces here that were pairwise incomparable. That was where Gasparis and Lung wanted to go. But now, okay, so the main step of what I did perhaps, or the first step, what I did with James, was that we observed, quite to our surprise, that this also works if you replace this with the other spaces I had over here. So it works for all of these. So this is for E equal to either these ones. That's not so surprising, but then it's also true for the Baernstein spaces, and I think that was a surprise. So my thought had been that, yes, there might well be an index that would do something similar to the Gasparis-Lung index, but I hadn't really imagined that, because the Baernstein definition is quite different, I hadn't imagined that the same index would work, but it did. So sometimes you're lucky, right? And so we get the same conclusions, of course, there. But now what we wanted to do was we wanted to use this to try and construct some closed operator ideals. And we could now take over the work we did with Tomek and Kevin and get to the continuum many maximal ideals. But also in the meantime, since I did that work, this method of Johnson and Schechtman had appeared for constructing 2 to the continuum many closed ideals, which is the largest number of closed operator ideals you can have on a separable Banach space, just by a counting argument. So let me just try and give you now a very quick introduction to the Johnson Schechtman construction, and let me give it in the form as stated by Dan Freeman, Thomas Schlumprecht, and Andras Shark. So Bill and Gideon wanted to do it for capital LP in the reflexive range, not 2 obviously, but then various people, notably Dan, Thomas, and Andras, they took the method and used it in many other contexts, and these guys here have stated in quite a convenient way, I find, in order to use for other spaces. So basically, the result is as follows. So you start with 2 Banach spaces, and they should have one unconditional finite dimensional decompositions. Bear with me for a second, and I shall explain that. The way, okay, so in practice, what we'll be doing is we will simply take our unit vector basis that's unconditional and we'll block it. So if you don't know what this means, don't worry about it. But the general terminology here is that these spaces here, say in the case of X, they have to be finite dimensional. And then the analogy with a basis is that for every vector in X, there is a unique sequence Xn with Xn coming from the nth space such that X is the sum from 1 to infinity of Xn, and this one converges unconditionally, that is the U, and this ensures that in particular for n, a subset of the natural numbers, just like you have basis projections associated with an unconditional basis, you have unconditional projections here, so you can simply define the projection that I'll denote by Qn, so that's the one that takes this expansion here, the unique expansion of a vector, and maps it onto just the coordinates corresponding to n. And the statement that this is one unconditional simply means that these are always bounded, but we are now assuming that they have norm 1, well provided, I suppose, this is not the empty set. All right, so that's a very quick introduction to one UFDDs. So we have those, and now, let's see, now the statement is, put that here to keep things together. See, we can, then the statement is that, well, suppose that there is an operator from X to Y with the following two properties. First of all, that it preserves the UFDD structure, so it maps the nth finite dimensional space in the decomposition of X into the nth space in the decomposition of Y. The second condition is, this is the more technical one, is that there is a lower bound on the distance from the operator, that is T, composed with the mth basis projection here, or mth projection here, to the ideal generated by T composed with Qn. So if you look at this distance, whenever M and N are subsets of N, and the difference between M and N is infinite, so this has to be greater than 0. Okay, so let's just take a deep breath and look at what this really says. Well, what it says is, so this, my angle bracket here, that means the ideal, just the algebraic ideal generated by these operators. Now I'm aware I'm working between two different Banach spaces, so this technically just means the subspace containing these operators, and with the property that if you compose from the right with operators on X, you stay within it, and if you compose with any operator from Y from the left, you stay within it. So it's just the obvious generalization of an algebraic ideal, but to this setting here. And what this says is that if M has a lot of stuff that isn't in N, infinitely much, then you can't really try to put this operator inside this ideal. Then it's too much sticks out in a uniform manner. Okay, that's the idea. So in other words, in particular, you can't factor these operators well through that operator there. That's the upshot of it. Now, okay, so now you take an almost disjoint family of infinite subsets of the natural numbers with cardinality C. So almost disjoint just means that whenever you take two different subsets in A and intersect them, the intersection is finite. So it's known since Sierpinski more than 100 years ago, I think, that you can find such an almost disjoint family of cardinality continuum. And then the upshot of all this is that if you now look at the map from the subsets of A, and of course there are 2 to the continuum many subsets of a set of cardinality continuum, and you take that to the closed ideal generated by these operators here for n in my chosen family, and you close it up. Now this is an injection. Okay, and again, so this is a closed ideal in the previous sense of up here, and because it's injective, then you have produced 2 to the continuum many of them. And in general, we shall use it just with x equal to y, but the reason I think it's good to state it in this generality is it highlights that you can do it with different spaces here. It doesn't have to be the same, but actually I'm going to apply it in a super simple case, because I'm simply going to apply it where x is equal to y is equal to my chosen space E from wherever it is up there, and my En, or rather my operator T, will simply be the identity operator, so that complication also goes away, and my decompositions here, they will simply be the span of the unit vector basis, or blocking of the unit vector basis. And the key thing, the only thing that we need to choose that is tricky, is we need to partition the natural numbers into consecutive intervals, Jn, and they will have to grow sufficiently fast in order to ensure that this condition is satisfied. So that's the last thing I want to try and show you, how, very briefly, one can try and achieve this. Okay, so this relies on another result related to the Gaspari-Schlung index. And this is what I thought was kind of nice to try and highlight. So let's see if I got everything I want to say at this stage. Yes, so, okay, so as I say, we've taken x and y are just either the Baernstein or the p-convexified Schreier space. T is the identity operator, obviously, well, and then xn and yn, these are just these, this is this blocking. So in other words, what I have is these consecutive intervals here, j1 up to jn, so they are partition of the natural numbers, and this is what I need to choose. And I'm sure Anna will recognize that the aim now, so this is what remains to choose these, and the aim is to get them to increase very rapidly, so they'll grow fast. That's how we achieve this thing here. Okay, and so the statement that we use for that is the following result, that for, say, a subset M of the natural numbers and an infinite subset, N, the following are equivalent, that the projection, the basis projection corresponding to M belongs to the ideal generated by N. That happens because we're working with projections. That in fact happens if and only if P has distance strictly less than 1 to this ideal. So in other words, as soon as a projection is close to an ideal, it actually has to be within the ideal. That's the key step here. And so this happens if a certain Gaspari-Schlung index, not M with respect to N, we have to fatten up M with N. So if this Gaspari-Schlung index is finite, and this happens by what we've seen before, if and only if this basic sequence is equivalent to the one indexed by N. So here we have again M union N, and finally this is equivalent to the subspace spanned by the vectors coming from M that embeds isomorphically into En. Anyway, what we want to do is we want to use of all those conditions we want to use, not C implies not B. In other words, if our Gaspari's lung index is big, then the distance is big. But we need to do a little thing extra before we are there, because we need to observe that, let's see. We need to translate between the basis projections and these finite dimensional projections, right? So here's the how I want to do it. So let me write Ln for the union of n in n of these sets Jn that I haven't told you how to construct yet. But this is just to have a convenient notation, because if I do that, then the finite dimensional decomposition projection associated with n will simply be the basis projection corresponding to this set. Let me just go over here and see that I believe what I said here, right? Remember, this one projects onto the blocks indexed by the j's, where n here comes from this set n. So this is just by having these blocks here that either you pick out everything in the jn block or nothing at all. So this is a translation between these projections and the two types of projections we have in play. And now, as I say, what I want to do is, because remember, I need this one here to be greater than 0. In fact, I'm going to show, so my aim is to show that if I get it right, that the distance, so because T is the identity operator and Qm is now PLM, and then this one has distance to PLN, so this distance is equal to 1 if M set minus n is infinite. Yeah, that's what I need to show. If I show that, then I'm good to go. Obviously, I don't need to show it greater than or equal to 1, because this is a projection of norm 1, so it can't be any bigger than 1, this distance. So that's basically what it means. And the way you achieve that is as follows. So you need your sets Jn to grow rapidly, and basically, so Jn will consist of two successive intervals, so Fn and Gn, and basically the way you do it is you construct by induction. You start with the empty set, and G1 is just the singleton set 1, and now if you've chosen the first n, then Fn plus 1 is simply the sum of all the previous ones you've chosen, and then you choose Gn plus 1 to be the union of n plus 1 maximal successive Schreier sets or Schreier intervals, because obviously, as I say, I'm looking for a partition. So I basically just say, well, I take this many elements in my next, that should be obviously the cardinality of Fn. These are intervals, so I know where I start. Then I collect that many numbers after that, and then after that, I then construct n plus 1 maximal successive Schreier sets just by counting up. And that's, if you do that, then now the key thing you can do is that what you get is that you can then show the following inequality. I think this will be the last thing I'll manage to say, that you get the following inequality, that the sup of m, take away n, is bounded by this Gaspari's lung index of Lm with respect to Ln. Okay, so remember the L's, they were these unions up here. So this gives you an upper bound on the elements of this set here. So of course, in particular, if I'm assuming that this set is infinite, then of course this is plus infinity. So this is plus infinity, and now by the fact that the Schreier families are spreading, this is actually less than or equal to this one here. If you make this family fatter, then the Gaspari's lung index can only go up. So altogether, what I have is that this Gaspari's lung index is plus infinity, So therefore, by the implication from up here, so this Gasparius-Long index was plus infinity, therefore this is equal at least 1, so it's equal to 1, just remembering that now I have an L on all of these sets here. Okay, and I think that's the end, and I'm out of time, so thank you very much for your attention.